Energy.
Um, Good evening, Mr. Prabhakar. How are you?
I'm fine. Yourself?
Yeah, I'm doing good. Actually, I'm traveling to attend a conference in Kyoto, so I have
Okay.
to do this class from the hotel room. So the setting has changed a little bit. Anyways,
You're in a
yeah,
hotel room?
yeah, currently in a hotel room.
Okay, fine. No issues.
So yes, so let's directly start the class. I have
Uh,
received
it,
your emails,
yes, yes.
and actually I didn't get time in the last one day to see the details, and also I couldn't understand in which part you are facing the problem with
Yes,
the week 6
yes.
problem. So
Okay.
the rest of the problem we are about to discuss today. So in that course, you can ask me that which part is problematic. We can discuss that again, and then
Yes.
subsequently in today's class, after finishing this topic, we will take on the deformation due to shear in
Okay.
beams,
Fine. Fine.
and
Fine.
then we'll finally go on to the code. So in the codes, I am planning to explain all the lines one by one. If I explain
Okay.
one code, I think the second code is pretty
That will
much
be fine.
similar.
Yeah, that will
Yes.
be same. That will be
Yes,
same.
I think this will be
Okay.
also important to see the scalability of the problem from a
Exactly.
simple
Exactly.
problem to a big problem, like in
Yes.
MATLAB, not rather not in MATLAB, like in StatPro
Scilab.
or yeah, SAP.
Stat Pro. Yeah.
Yeah, yeah. Anyway, so let's get started with the class. Um,
Okay.
so
On the same problem, Mr. Banerjee,
yes,
let me
this was
for
the
this
uh,
column member, whatever that member BC, go back to that
BC.
sketch. I want to understand what is that
Okay.
vertical member. Is it BC or AB? It is AB.
AB. Yeah.
Okay.
Okay. Hmm.
Okay. First
Yes.
doubt is
Hmm.
when we are writing this transformation matrix. Okay,
Yes. Hmm.
we have to write as per that degrees of freedom. That is in that 1, 2, 3, 4, 5, 6 order. If I'm correct,
Okay. Yes. Yes. Hmm.
correct.
Yes.
Because I never wrote those degrees of freedom and transformation matrix. So blindly I was writing something. Suddenly I got that doubt in my mind.
Hmm.
So if I understand correctly, it has to be with respect to the degrees of freedom 1, 2, 3, and 4, 5, 6.
Yes. Correct. Hmm.
Correct?
Yes.
Because
Hmm.
degree of freedom one is with respect to x, that is that lambda x. Two is with respect to y, lambda y, and that third one, or that three.
Yes. Yes. Correct.
Correct?
Yeah.
My second doubt, is that order is right? 1, 2, 3, 4, 5, 6 transformation matrix, whatever I told on that lambda x,
Um.
lambda y.
Yes.
What is
Means.
that? Our standard transformation matrix lambda x, lambda y, 0, 0, whatever is that. What we get that lambda x into lambda
Hmm.
y,
Hmm.
correct?
Hmm.
For that
Hmm.
beam element.
Hmm. 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 Okay. Let me
So,
open the number two element. This one. Yes.
yes,
Yes. Not number two. Number one element, right? This one.
number one.
Yeah. This one. Okay.
Yes.
Hmm.
So 1, 2, 3, 4, 5, 6. Okay, that
Hmm.
is clear. So always that lambda x is always with respect to x-axis, if I'm correct. That initial node
Yes.
with respect to x-axis,
Yes.
global x-axis,
Yes.
correct? And
Yes.
then is the global y-axis too, and then the other one is that moment value,
Yes.
correct? So
Yes.
if I take that okay, even with the beam element 2, even that go to that beam element 1, that
Yes.
problem, because
This
I'm
one.
just getting beam element 2. Okay, in this, okay, again that 4 and 7 is with respect to lambda x, that is global x axis.
Yes.
Then comes 5 and then is 6, correct?
Mm-hmm. Hmm.
So in the
Yes.
same order, I had to write the transformation matrix.
Yes.
Clear?
Yes. Yes.
Okay, then I can do the transpose. Okay, that step is fine. Now go to that element stiffness
One.
matrix for 1. Okay,
Yes.
this
So,
is 2.
like, let me guess if I am
Uh,
understanding correctly what you're trying to say. You're trying to say that this is the element, and we have the degrees of freedom like this: 1, 2, and 3, then 4, 5, and 6. So 2 and 5 would be the actual degree of freedom,
Yes.
and 1 and 4 would be the beam. one
Vertical
one
display, vertical deformation. Yes.
Yeah, 1, 3, 4, 6 would be the beam deformations. 1 and
Yes.
4, 3
Exactly.
and 6. You are telling like this, right? But when we write
Yes.
the stiffness matrix, we take AE by L in the first row and
Exactly.
in the fourth row. This is what your,
First row, first row, first column in the standard element stiffness matrix is A by L.
yeah,
That is for the
yeah,
axial stiffness.
yeah, like this. We take AE by L in the first and fourth,
Yes. Yes.
like this. So you feel that this is like this should be interchanged in this case, right?
Exactly. Exactly.
Yes, yes, yes. So okay, so the thing is, um, that is where the transformation matrix comes into play. So actually when we write the stiffness matrix, element stiffness matrix, without the transformation matrix, we actually assume this as 1, this as 2, this as 3, this as 4, this as 5, this as 6. Okay. Now when we use the global degrees of freedom, we transform this 1, 2, 3, 4, 5, 6 to the new system, to the global system. So what actually happens is,
Mhm.
here 1 becomes like, here the 2, original 2 becomes -1, and the original 1 becomes 2. Okay. So let's see over here. Yeah. So here in the stiffness, in the transformation matrix, after, if you check with this, like if you do this T transpose K1 T, and if you do the matrix evaluation, it will actually interchange whatever there was, that will be interchanged. uh, I can show you here. So this one is the element stiffness matrix without the transformation matrix, right?
Mhm.
And this one is the element stiffness matrix with the transformation matrix.
Okay.
Okay. Now check the first and second rows of these two matrices. They are actually interchanged. And not only completely interchanged, also the fourth degree of freedom is also shifted. Fourth and fifth are also interchanged. Third and which one? Fourth and first. Here you see 0, 1, 3, 0, -1, 3. 1, 0, -3, -1, 0, -3. Okay. And this one, which was like 1, 0, 0, -1, 0, 0, that has become 0, 1, 0, 0, -1, 0. That one actually has come directly to 2 and 5, because currently now 2 and 5 is our axial deformation.
Okay.
Okay. So by doing this transformation, we are actually bringing this system to this 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6 degrees of freedom. Actually, when we write the stiffness matrix without the transformation matrix, it is the red one, and when we transform it, it becomes the blue one. So there, we should not confuse our global degrees of freedom with the local stiffness matrix. This is the local stiffness matrix. In the local stiffness matrix, I have written 1, 2, 3, 4, 5, but this is not the global one. This is the local one. This is the local one.
Mhm.
And
Exactly. That is where I was getting that doubt.
yes, yes, and these are the global one. So in the next part, what happened is, because it was the global and local is the same, so the same one worked. But in the first case, the element stiffness matrix is first defined in the local level, then in the global level. Okay.
So you mean to say that,
Yes.
I mean, better way to understand this is that the
Hmm.
degrees of freedom, whatever you are writing in the standard beam element, 1, 2, 3, 4, 5, 6,
Hmm.
instead of telling it is an axial stiffness, vertical deformation and moment, can
Hmm.
we say that forces in x direction, y direction, and the moment that will be better than because I will get confused if we say that in the standard beam element stiffness matrix,
Hmm.
always degrees of freedom in one is for axial stiffness,
Okay.
AE by L, AE by L
Yes.
it is
Yes. Okay.
for beam element. Say for example, beam element 2, that the degrees of freedom 1, it is an axial stiffness, AE by
Okay.
L. That matches for the beam, which is in horizontal direction. When
Hmm.
it comes to
Yes.
column,
Hmm.
that if I call that as a degrees of freedom 1 in x-axis, that is becomes the stiffness for the what you call vertical deformation, and degrees of freedom 2 becomes a axial stiffness value for the
Hmm.
columns.
So, one thing here is when we are talking about axial stiffness and vertical stiffness and rotation, that is
These
in
are
the
the
local
forces.
system.
Basically, the forces. Yes, just
That,
it is
that
forces in that.
yeah, yeah, any forces or displacement that is in the local system, in the element level, in the local level. Whenever the beam, there is transformation to that beam, the beam becomes a column or anywhere between a beam and a column. It can also be a slant member, right? So in all of those cases,
Hmm.
we cannot define these 1, 2, 3, 4, 5, 6 as axial or vertical or rotation. Rotation will always be the same, 3 and 6, because rotation
Same.
is in the
Yes.
other plane. But
Correct.
the axial and vertical then becomes like problematic, because if it is a beam, then it is same as axial and vertical.
Exactly.
If it moves away, it gets slanted. So in that case, what happens is the components work. So there is axial component and vertical component, and when it directly
Hmm.
becomes a column, then everything rotates, like it interchanges. So so in the element stiffness level, it is, I think, okay to call it axial and vertical and rotation. The reason for that is it gives you more clarity on the stiffness matrix in the element level. You are not memorizing the stiffness matrix with the
Exactly. That is where the
transformation
problem
matrix.
comes. That is
Right.
where the problem comes.
Yeah.
See, I'm not memorizing that. Go to that element 1. I'll tell that
Yeah,
problem.
yeah, yeah.
Go to that element 1.
Yes.
See, in this, if you keep this, I'll
Yes.
think that, okay, degrees of freedom 1 means,
Hmm.
I think that that should be 12A by L square, L cube, that one.
Okay,
Because
okay,
it,
okay.
it gives the,
uh,
and
so
degrees of freedom 2 and 5 is for AE by L. That is what,
okay.
I'm,
Yeah,
that
I
is where I'm
understand.
getting.
I understand. So another what thing has happened is this is a very special problem, right? Here, the first element, first member has become a column. Okay. So all the degrees of freedom that are named from the first member, they have actually interchanged. This is a special kind of problem. So what we have to do in this case is, like, this transformation matrix, we are writing this as the global degree of freedom system. Okay. But this stiffness matrix, local stiffness matrix, this is the local degree of freedom. So you need to, so what would happen if we number this as 2? If the this member becomes 2, the column members become 2, and the other member becomes 1. So um, say we start from here. Okay. 1, 2, 3, then 4, 5, 6, then 7, 8, 9. Okay. So in this case, what would have happened is this element stiffness would have remained the same, but here it would have been 789456. 789456.
Correct.
Yeah. So we need to keep in mind that here also 789456, 789456. So here we have to keep in mind that which matrix we are writing in which sense. Like the transformation matrix and the global stiffness matrix are with the global degrees of freedom, and the local stiffness matrix, I maybe you should also like skip writing the degrees of freedom for the local stiffness matrix, because it will be same, it will be 1 2 3 4 5 6 for every member. There will be no difference for any
Okay, then
member.
I have to just put that AE by L 12 I just have to write that
Yes,
for
yes,
local
yes,
stiffness.
yes. Just the values of AE by L and those things. The degrees of freedom don't matter here. But when you use the transformation matrix and transform, then the degrees of freedom come into play. And why, like, without any consideration to the degrees of freedom, you are means why can you use the same element stiffness matrix? The reason is the information on the degrees of freedom are already carried by the transformation matrix. Here if you change 4 5 6 and 7 8 9, your transformation matrix will also change. Okay.
Hmm.
So that will take into consideration of like what kind of final matrix you are getting.
Hmm.
Still confusing?
I'm slightly probably what
Yes.
happens if you take that assignment 6. I
Mm-hmm.
still believe that answer might be something wrong. I don't know. I'm just guessing because I'm not whatever the uh, permutation combination I do. I'm not getting that answers in that current. I mean assignment 6
Uh,
problem. I'm
but
not
the
sure
like
where I'm doing wrong.
solution is given, right? So in the solution
Solution
did
is
you check?
they're directly given the matrix. They're not given the transformation matrix or transpose of that, and they're not given the solution. They're directly given that matrix for that global stiffness for that element two.
Okay. Okay. Okay.
So
So maybe what can be done is, in this case what
mhm.
can be done is like you can solve this problem in your way, and you can send me a scanned
Okay,
copy of your solution, and I can
okay,
just go through like if there are any conceptual mistakes in that, and if not,
sure.
then I have to check like what is the problem with the solution
No,
also.
no, no, no problem. I'll
Mm.
just again go through that assignment 6 problem. I'll write it again. Okay,
Yes, yes,
I will
okay,
scan it and I will send it to you. Okay,
okay,
so
okay,
then we will see that probably next week we can discuss on that
okay,
whatever
yes,
is there. Next week
yes,
will be
sure.
any classes will be there or today is the last one.
No, next week is the last class. Yeah.
Next class. Okay,
Hmm.
we'll discuss in that next
In
week.
next class.
That
Okay.
not an issue on that particular because again
Hmm.
that confusion is okay. When I'm
Hmm.
writing the stiffness local stiffness matrix, I always think
Hmm.
that okay, grid. I mean vertical deformation, axial stiffness. I remember in that way to
Hmm.
put
Hmm. Hmm.
those stiffness values. That is
Hmm.
where
Hmm.
probably I'm doing wrong. But
Hmm.
anyway,
Hmm.
we'll discuss that next week, Mr. Paras.
Okay.
Not an
Yeah.
issue
Yeah.
on that.
Yeah. Sure. So, just continuing and completing our discussion from last class, it was like
Mhm.
now we have got the partition stiffness matrix, right? So,
Correct.
so here we have the unknown displacements and the unknown forces. So, these are the known forces Pk, these are the unknown forces Pu, these are the unknown displacement Du, these are the known displacement Uk, and these are all zero. Okay, so even in the truss problem what I saw is the known displacements have to be all zero to that program to work. Okay, so if you have any known displacement which is non-zero, so you have to write a different program for that. Anyways, the like idea of giving the program was not to give you a foolproof solution of every kind of truss, but to give you the idea on,
Guidance. Just
yeah,
this.
yeah, to give you the idea on how to develop programs. Anyways, so now solving this from here, what how we solve is now P4 P5 P6. Let's go back. What is P4 P5 P6? Mm, yeah, okay. So P4 is 0, P5 is 0, P6 is 100, right? From this problem. 4, 5, 6 is the that joint forces. So if we do P4, P5, P6 equals to, please also simultaneously check if I am doing anything erroneous or not. This was what we had achieved from the last class. This was the, yes, 456 456. Okay, so P4 P5 is 0, P6 is 100, equals to 203,023,3324, U4 U5 U6. Okay, so now we get the solution of U4 U5 U6 as how much? We get it as minus 10 minus 10, 6.67, and everything is in units. Okay, I think the problem was defined as in units. So now how we will calculate the unknown forces from here? To calculate the unknown forces, you take this matrix P PU, which is P7, P8, P9, P10. Oh, sorry. P1, P2, P3, right? Yeah. P2, P3. And you have the stiffness matrix over here, minus 1, 0, 0, 0, minus 1, minus 3, 0, 3, 6, minus 1, 0, minus 3, 0, minus 1, 0, 3, 0, 6, and you have the U4, U5, U6 from here. Okay. So this part is understood, I guess. This we have already done in all the methods.
Yeah, this
This
is clear.
is,
This is clear.
yeah,
This
P
is clear.
unknown equals to this matrix into the unknown displacements, which are now known. So the answer for this would be 10 minus minus 10 plus 10 minus 10 10 10. This is what the answer is written in my notebook, and you can also check after you solve it by yourself. Then similarly, now you can find the different forces at the different element levels, so that you
Yeah,
can
that you have
do
to use that
using
element matrix. That you have to use
element,
that
yeah,
element matrix.
you
Yeah,
can use the
fine.
element stiffness matrices, and you can find the different forces at the element level.
Agreed.
So
Agreed.
yeah, so I am not like reiterating that process that is already done. And also the reason why I am not reiterating is, here all the forces are joint forces, so there is no point of like fixed end
Agreed.
moments or anything.
Agreed.
So
Agreed.
this is like pretty much similar to your truss problem. Okay.
It is not required. Even with this force, you can directly put that bending moment diagrams for this
Yes,
and shape
yes,
diagram.
yes, yes. So that part I am skipping because we have already covered that in the truss class. Okay. So now moving on to your next issue this week, that is the uh, first we'll discuss about the deflection due to shear, and then we'll go along with the different problems, different Skylab problems, Skylab codes. So now before we start the deflection due to shear, so now matrix method, apart from that problem, that one issue of the frame element, which we will discuss later through the solution that you are making. So apart from that, everything is clear, right? Is there any doubt?
No, no, no. That is
Okay.
clear. Probably
So
different books I mean explains in different ways.
Huh.
And because I was just going through that one book from Mr. Devdas Menon, I mean,
Hmm. Hmm. Hmm.
he takes some different approach in putting those uh, force matrix
Okay.
in that.
Hmm.
He puts that action forces and reaction matrix, so in different way, but concept wise it is clear. You'll get the same answer whatever the way you do it, so you'll get the same
Yeah,
answer.
yeah, yeah, yeah.
So that,
Exactly. That is the like main objective. Like you develop your own concept, and then you stick to that. It's not that you just change. So anything you take and you stick to that. It's pretty much similar to the sign convention that we take. You take one and then stick to that. So I think you will always get the correct results with that method. So now,
agree, Mr. Yeah.
yeah. So now then, discussing very briefly the deflections due to shear. So
Is that the okay? One more question: is that the
yes.
same way how we apply these temperature loads also in this analysis?
mm,
How
Temperature loads also you can find through this method. Yes, that is correct.
how do
And
we put those the temperature loads at the, I mean, as a nodal loads?
so temperature loads, it is like so today I'll briefly discuss about the energy method to find deflections, because shear deflection, what happened in the bending deflection is we use the elastic beam theory, and
Correct.
then the curvature of the beam is same, and those things, all the assumptions we used, we considered the beam to be elastic, and then we got very nice equations, and we directly solved those equations to get the deflection. Okay, because of the nature of the curvature and those things. uh, and in case of axial, we are being doing axial deformation, we are handling, I guess, from our school level, like what happens when a bar is being pulled downwards
Now, that
by
concept wise it is fine, but how
p
it is
force.
implemented in our stat software in the matrix methods?
Okay, yeah, coming to that. Yeah, so now so how, which one is implemented, like the temperature loads and those things you are talking about?
Yeah, because if you are designing some structures in extreme cold or extreme hot conditions, okay,
Okay.
we are going
Hmm.
to define what is that difference in temperature and its thermal coefficient, okay.
Yes, okay. Hmm.
And sometimes what happens, we just put a expansion bay and we neglect this temperature analysis, okay, as
Yes.
per Indian code whatever it gives. If you are
Hmm.
giving the expansion bay at 50 60 meter, I mean, I don't remember exact that number. If you are,
Hmm.
I mean, following that guidelines,
Hmm.
it, IS code clearly says no need to do this temperature analysis
Hmm.
for
Hmm.
that.
Hmm.
But for if you are doing it for some abroad client, like if you are doing
Hmm.
some projects in Kazakhstan where the temperature goes to minus 30, minus 40, material becomes
Hmm.
brittle, or if you are doing it in Saudi, the temperature goes up to 50 degree because the design temperature they gives up to 55, 60, whatever is that.
Hmm. Hmm. Hmm.
So at that time, I mean, some time client asks us, okay, you consider the temperature variations in the analysis.
Hmm. Hmm.
So STAT has got that option of providing those temperature variation between the top and bottom flange, outside and internal. So everything we can give that
Hmm.
in that. How it
Hmm.
calculates, I mean, not sure in the
Hmm.
STAT
Hmm.
how
Hmm.
that will be implemented in this as part of because there also, I mean, for that problem also STAT does only the matrix method only for analysis.
Hmm.
So
Hmm.
I can understand the elongation constraints, everything we can, but how that load gets converted into nodal loads in that. So that
Hmm. Hmm. Hmm.
something.
Hmm. Very interesting. So now, yeah, very very interesting question, and very, like, it is also interesting for me, because frankly speaking, I am not an expert
I
like
understood that. I'm not expecting. I'm not expecting.
uh,
I'm just putting
yeah,
that
yeah,
in your
yeah.
brain so that you
No,
just think and come in. Because
yeah, of course, no, no, like, I am happy to, like, get this question so that we think and we find out what happens. So basically what happens in temperature kind of loads is, I know, uh, as for STAD, um, like when you give temperature, I'm not sure on how to give temperature loads in stat, but what I assume is you define a room temperature and you define a
Very,
uh,
yes, yes,
outside temperature.
yes.
So so now there are also many problems in that, you know. So so when the temperature changes, like a temperature does not randomly directly goes up
See,
to the
for
55
example,
degrees Celsius.
for building it is fine. Inside, outside, you can give it.
Yes,
For
yes, yes.
what happens if it is an open structure like pipe racks or cable rack structures, whatever is that, all surfaces are exposed to that much
Hmm.
temperature. There is nothing called inside or outside because all that
Hmm.
surface experience the same temperature increase.
Hmm. Hmm. Hmm.
Okay,
Hmm.
variation will
Hmm.
be
Hmm.
from 20 degree to 50 degree.
Hmm.
Okay, there will be variation of 30 degree. That is what you have to specify in stat.
Hmm.
What is that variation we are expecting on the structure? Plus 30 degree, minus 30 degree, whatever is that. So
Yes.
probably what I think for axial member, probably it takes that the variation in temperature, multiplies it by thermal coefficient, and probably does some back end some forces and it incorporates in the designs or
Exactly, you
analysis.
are right. Yeah, yeah. Exactly. So not only for axial members, for oh okay, yeah. By axial members you means beam and column, like longitudinal members, right?
Anything in axial direction, yes,
Uh,
longitudinal axis.
yeah, means it depends, like how temperature acts on a body. You, if you can visualize that, the stat and other softwares, they just change that to equations. Okay, so maybe for example, let's see, this is a okay, no, let's take all kind of members.
Just take a portal frame, whatever is that, portal frame, cable frame, whatever is that. So then,
uh, let's take a building kind of structure. So
yes, anything is fine. Yeah.
yeah, so something like this, these are columns, and then there is the slab also.
Yes.
Okay, so now when you expose any member to temperature, basically what happens is its volume kind of changes. Okay, so either it expands if you increase the temperature, or it contracts if you decrease the temperature. Okay,
Yes.
so now what happens for longitudinal members, like say columns, the volume change in the direction of length is much higher as
Is
compared to
exactly.
any other
Yes.
thing. Yeah, and if you take some members like say slab, the volume change in the direction of this plane, the plane of the slab,
It
is
will be less.
much higher than the like change in the thickness. Okay, the thickness change will be
Thickness,
negligible.
exactly. Yes.
Yes. So but basically what we are trying to do is we are changing the uh, volume of the member. Okay, so in that process, if we know the thermal coefficient of the columns and slabs and materials and everything, and if we know the change in temperature, we can find what is the elongation or compression. Elongation or
Exactly.
compression. So in column members, it will be only elongation and
Elongation. Mainly, it
compression
will be
in
elong.
one direction, in the longitudinal direction. In slab members, it will be in two directions in area.
Exactly.
Okay,
Yes.
so basically what STAD does is they incorporate this elongation or compression as the what to say, joint and displacement kind of thing. Like in that, like the joint is still fixed, but then there is a elongation. So there is a tension that is
Exactly.
developing. If it is elongation, then there is a compression that is developing in this column. Okay, so basically, like you can say that there is either a compression or a elongation. Then like what's the need to uh, get into so much depth, um, because there will be slight compression or tension, right? And we are,
Mhm.
uh, as per se, we are not very like what to say, worried about the compression or tension. But what happens is there are certain limits to what we are not worried about the compression and tension. If the compression becomes very high, like if the temperature becomes very high, then the compression will be more, more and more, right?
Mm.
So then
Mhm.
there could be some buckling kind of failure of the column also because of the high compressive load, which we
Why
might
do you
have.
think it is a compression? Why do you think it is a compression load? What happens if it elongates in vertical direction? Like it's a tall structure, just
Yes.
like it is a cantilever, it expands in vertical directions. It may
Okay.
create tension.
Yes. Yes. So, no, it will not create tension. Uh, if say this is a fixed kind of structure, the column is
Okay.
basically a
Mhm.
fixed kind of structure, right? When we develop the stiffness matrix, we assume that
Agreed.
both ends are
Agreed.
fixed, right?
Agreed.
So now
That's
if
what I said. What happens tall structure like a cantilever structure? It
um,
expands in vertical directions.
okay, it expand in vertical
Then we are.
direction.
It takes tension. It takes tension. It will be subjected to tension.
I'm not sure whether it will be subjected to tension. A very tall structure.
See, for example, what happens if it is a cantilever column?
If it is a cantilever column with one end free, I can understand it will be only
Yes,
elongating
exactly.
upwards.
It elongates.
Yeah.
Same concept in the tall structures. When it is length and breadth are less,
Yes.
depends
Yes.
on its geometry. Okay, it acts as like a complete
Yes, but
vertical.
it is not that easy, I guess, because
Exactly the problem. See, whenever you get the temperature analysis, we'll get into some problem. Okay,
no, it is not
always.
that simple that it will elongate in one direction. The reason is most of the mass of the structure is like concentrated in its slab, right? So most of the weight is coming from the slab, and so the fixity of the joint is maintained by the slab itself. Okay, so there is for a cantilever beam there is no concept like lumped masses, right? There is only distributed, uniformly distributed masses. So
No,
if
no.
you yeah.
And when I say you are assuming we are discussing on some building where you'll have a lump mass from the slab. Okay. What I'm
Hmm.
telling, that is okay, agreed for a residential commercial. What happens
Hmm.
in our industrial structures, what happens? For
Hmm.
example, if I have some reactor vessels which is 90-meter, 100-meter tall, we are going to
Ah,
build
okay.
some
No.
operating
There, yeah,
platforms
obviously.
around that. There won't be
Reactor
any
vessels, then
masses.
chimneys,
There won't
and
be any masses. It
those
will
things.
just it's
Yeah.
the operating
Hmm.
platform which goes till 100-meter height.
Yes, yes,
Their
yes.
gravity load will be less. Okay, you can assume
Yes.
some live load, but live load will not be there. Always live load will not be there. Only will
Yes.
have some dead
Yes,
load of
yes,
grating,
yes.
handles,
Hmm.
everything. So there won't be
Agreed.
much dead weight on that.
Agreed, yeah. So then there would be some elongation in the vertical direction.
It's
Absolutely there
possible.
would
I
be.
mean, both ways it. I mean, it is
Absolutely there would
depending on
be,
the
and
load. It's compression,
uh,
tension. It depending on its geometry, basically, and
yeah,
the load.
geometry and load exactly. And what happens is that from the difference in temperature and the coefficient, the thermal coefficient of the material of the members, they actually calculate the elongation or compression, and they put that vis-a-vis the restraints in the structure. So say there are some there is some restraint around the container or something. It is fixed around some point, so all the stresses will be generated at that point itself. Okay.
Mhm.
So there would be extra joint loads there. So that is how there would be
Exactly.
that is how they
That
like.
is what I'm trying to understand. How they calculate that nodal loads for those things, and also it is not as simple as that. Say, for
Hmm.
example, whatever the picture you are drawn here. Okay,
Yes. Hmm.
if you are applying a temperature load, what happens that
Hmm.
at the floor level,
Hmm.
both
Yes,
in
yes.
beams in the x and z direction, will have
Hmm.
a different length. Okay,
Pardon.
if
Just
it is
just let
both in
me
x and z
write
direction,
what is x, y, z, and then I will be clear. Yeah. In what
okay,
direction? X and Z direction.
I mean, floor level, x
Yes.
direction and z direction. If it is a square in shape, it is fine. Both
Ah.
lengths will be
Yes.
same.
Yes. 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 Hmm. Hmm.
If it is rectangle, what happens? Both beam length will be different.
Yes. Yes. Yes.
And if
Yes.
you apply that thermal coefficient,
Elongation would be
what
different.
happens?
Hmm.
Different.
Hmm.
And what it does, it creates some kind of a torsion on the columns at wherever it is
Hmm.
connecting.
Yes. Yes,
So
agreed.
sometimes it is very difficult to, I mean, visualize what is happening in the structure. Whenever we does this temperature analysis, we'll get into some one or the other problems.
Hmm.
Either
Okay.
will not be applying properly
Hmm.
the loads, because sometimes probably we have to ignore the temperature loads on the member less than 3 meter, 4 meter. Probably we have to ignore that in when we're applying the temperature load, because that avoids all these eccentric loading on the column due to these expansions of the
Hmm.
different thing. Probably we have to apply those temperature loads only where you got a member. For example, if that column is going up to 70 meter, 80 meter, probably we have to apply that only for those particular members to allow only expansion in the
Hmm.
vertical. I mean, that is what always we get into that problems always
Hmm.
when
Hmm.
we
Hmm.
does this temperature analysis in a stat.
Hmm. Hmm.
Okay,
And
so
one
normally
more
that is
thing.
not one of the cases. It is not every client will ask for that.
Yeah, yeah, yeah,
So,
I understand. And
so
like one of the thing which we which I like felt during this discussion is that what happens in buildings, in residential buildings or office buildings or any building kind of structure, the redundants are so much more that most of the joints are fixed, like the
exactly, I agree with you.
yeah.
I agree with
So if you like temperature analysis is comparatively easier because you can just increase decrease the length and then incorporate the tension compression. But temperature analysis is actually necessary in any structures which are less redundant. Like bridge structures have much less redundant than building structures. So therefore the bridge structures, there are those expansion joints, more of those expansion joints and
you.
those things and
There
lot.
it won't be any problem because we will be providing some roller supports at that one end.
Yes,
When
yes, that
we
but
are
that
done with
is
that temperature, there won't be any problem.
yes, but that is due to the fact that temperature becomes a issue there. Okay, but for building structures it is not a issue. So that is correct. And for any
Nobody will
other
ask for the building, for the
hmm.
small buildings and all. Nobody will ask for that.
Hmm.
Especially this problem, what I explained.
Hmm.
As I said, for some pipe rack which runs into some kilometers, anyway, we'll be providing
Yeah,
that expansion
yeah,
gap
yeah,
up
yeah.
to 70 meter, 80 meters
Hmm.
by
Hmm.
default. As per the whatever that the local code specifies, we'll be giving that expansion
Hmm.
joints there.
Hmm.
IS code very clearly says if you are providing this expansion gap at these intervals, no need to do any temperature. That is very clearly written in that IS
Okay.
codes.
Hmm. Hmm.
Same thing is not specified in whether it is an American and Europe code, but I may
Hmm.
be wrong. Probably someone, one or the other class might be written like that, but they're not very clearly written in that way.
Hmm. Hmm.
In that case, what happens? Client will ask, okay, demonstrate that this structure is good enough to carry this plus or minus 30 degrees variation of the temperature. This
Hmm.
is steel.
Hmm. Hmm. Hmm.
So at that time, what happens? We try to put those values in the stat, and I mean, we'll get a
Hmm.
lot of other problems because we'll not be able to visualize how we are getting the forces in the members, because some columns may get some torsion,
Hmm.
tension, compression. We'll not be able to visualize that. If it is a regular dead load, high load, we know that which member
Hmm.
has to carry which force, tension, compression. By default, we know that.
Hmm. Hmm.
Okay, this column, okay, this is brace structure. If it is strong, okay, this column has to come tension, this has to under compression during dead load, or if it is live load, these forces may reduce. All that we can visualize.
Hmm. Hmm.
At least when we are cross checking the design, we know that with it, this is tension
Hmm.
compression. If there is any slight variation, we'll immediately go back to that
Hmm.
inputs and
Hmm.
we'll
Hmm.
verify
Hmm.
that.
Hmm.
But when it comes to temperature, I mean, we have to accept whatever stat is giving. We are in that stage.
Ah, okay, okay, okay. So, basically now we are talking about like big pipeline kind of structures.
Yes, it will
Ah,
be
okay.
some 70-meter length and width will be 3 meter, 4 meter, having a multiple tiers
Hmm.
up
Hmm.
to
Hmm.
10 meter height or whatever. You understand
Hmm.
what I'm talking? Pipe racks structures. So that will be a
Yeah, like
huge.
pipes and then joints of pipes and those things.
Yes,
So,
yes.
so
I'm
any
not talking the pipe. Where the pipes are supported on a steel structure, it will be a huge
ah,
steel
okay,
structure will be there.
okay, okay, okay,
Anyway,
okay,
pipe we are not bothered. Pipe they'll have some different tools. They'll do all that analysis for the pipes. It is.
okay.
I'm not talking the pipe. I'm
So,
talking a structure which support these pipes. there will be huge structures will be running kilometers.
Oh, I understand. I understand. Hmm.
There is a gas
So,
pipeline,
okay, okay, I understand.
those
So you're
structures.
talking about the like effect of temperature on those truss kind of
Steel
structures, like
structures. I'm not talking about the pipes. It is. I'm
yeah,
talking about the
yeah.
steel structures.
Any kind of truss kind of structures, and then the pipes
It
go
will be
along.
lattice. It will be lattice. Yes, it will be lattice kind of a structures,
Hmm.
and somewhere will be so those kind of a thing.
Hmm. So the expansion and compression of this truss kind of structure you're talking about, right?
Yes, yes, yes.
Okay, okay.
And if you're not putting that properly, then due to difference in temperature, that creates somewhere in some member some torsion forces,
Hmm.
and it will be showing okay this member is failing by torsion, or if we check some utility ratio, it will be more. So we'll not be able to visualize that in
Hmm.
this
Hmm.
SCADA. Unless we know how it is acting, these forces, we'll not be able to visualize how we are getting those forces on the members. General, that is the
Hmm.
thing.
Yes, 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 yes. Yes, okay.
You can
Very.
take some time, okay? Sometimes in future, if we anyway permits, we can discuss on that, Mr.
Yeah,
Panash.
yeah,
That's
yeah, sure. But like basically, temperature loads, what we means, what happens is that the elongation and compression occurs, and then at the joint, the forces are like induced
exactly.
due to the elongation and compression. So now everything depends on the kind of structure, that what is the
Yes,
shape of the
yes,
structure and the different aspect ratios,
yes, yes,
basically.
yes,
So
yes,
depending on the different aspect ratios, you will get the torsion and those things. So
yes, definitely.
yeah, yeah, yeah.
So
So
probably we have to simplify the analysis by not putting those temperature on smaller members, small length. Probably have to put only for the longer members. So some kind of thing we have to do that. So
so
then only
one
we
thing
get that.
out of the blue, one thing which came into my mind is like, if this is the structure supporting the pipes, right? So there
Yes.
would be some repeatability in those structures, right?
Hmm. Yes, yes, yes,
Like
yes.
there will be blocks of different
Yes,
trusses.
definitely. Those are all modular kind of a thing. I mean, we have to fabricate only 60-meter length in length, and we have to keep
Exactly.
placing those things.
Yes,
Yes,
yes, yes. So those blocks, what happens is the temperature variation in these blocks are
hmm,
actually same, if
yes, yes,
obviously considering the temperature is constant throughout the structure.
yes,
Yeah.
yes.
So the temperature variation of the blocks is same. So what we can do is, you can analyze one block where you have
Hmm.
the different truss kind of structures, and you can
Yes, yes,
find
yes.
what are the nodal displacements and everything. Then
Hmm.
using those nodal displacement, you can take one axial element representing that block, and then you
Hmm.
connect many axial elements together, and then you see what happens to that axial, to that continuous kind of structure.
We'll see.
Um,
I need to do some R&D on that. Okay. I
yeah,
think
yeah,
I'm
yeah.
just.
But like, does it make sense? Because I am not sure, I am just discussing this. I think this could make sense is like, if you take, generally in research also, what we do is, there are many complicated things which we simplify. So one simplification of this thing would be to analyze one block very nicely, find the
Mhm,
displacement of the block for that temperature. Then next time you arrange those blocks together, say, these, you have different joints of the blocks, like this, like this, like this,
mhm,
maybe
mhm,
upward, anywhere. You arrange those
mhm.
blocks together, and then you don't apply temperature or anything, you just
Put
induce
some axial
like
forces.
tension
Induce.
or compression in those blocks, and
Mhm.
then you see that where this joint is moving, how it is moving, and what is happening, and those things. So
I think some 8 9 years back I think we did that exercise on
okay.
the way what you're telling.
Yes, yes, yes.
Because at that time we couldn't able to see, I mean, check results this properly. So what we did, we
Mm-hmm.
took the temperature forces only on that long members like beams or columns, and we
Mm-hmm.
calculated physically what is that force, like alpha,
Mm-hmm.
LLT, or whatever is that. That gives the elongation, and
Mm-hmm.
with that elongation, we back calculated what is that force it is going to generate. So we put it as
Mm-hmm.
a nodal force, and we analyze that
Mm-hmm. Mm-hmm. Mm-hmm.
structure. That is what. we did
Mm-hmm.
long
Mm-hmm.
back. Nowadays, what happens? I mean, clients are asking, when STAT is there, why you want to do all that calculations? You directly put those values
Ah,
in STAT.
yes, yes.
So all that things
Ah. But
creates.
also like every time you cannot like blindly also follow the value of stat also. So one other way is
Exactly.
that you can try in some other software also, and then if both the softwares give you similar results, then you have some confidence. Like sometimes things become kind of black box, right, when we do more and more
I know.
computation.
That's the reason I raised. That's the reason I raised this point.
Yeah,
Now
yeah,
that
yeah. Yeah, to
if
one
this
way to verify
analysis.
that is like you can check this with some other software also, that is possible.
Let's see.
Mm. Yeah.
Sorry, I dragged into some other topic, Mr.
No,
Banerjee.
I really enjoyed, like frankly speaking, I am very inexperienced in these practical issues. I have been only doing research directly uh, after my undergraduate and postgraduate. So I enjoy discussing about these issues, and I have also learned a few things from this.
Okay, thanks.
So
Okay.
yeah, so no problem. So moving on. So now uh, yes, so we were discussing about the deflections due to shear, right? So
Yes.
currently, what we have considered in our frame matrix and in the matrix methods of frame elements, beam elements, truss elements, we have checked two kind of deflection. One is the axial deflection, that is for the truss, axial deflection for the truss, and then there is the vertical deflection and rotation, but for bending and not for shear. Okay, axial and bending, but so hello.
Yeah, I'm here. I'm here.
Okay, you are here, but I cannot see my handwriting on the screen.
Exactly, exactly. I mean, I was about to ask you that because I thought there is some lag in the because you said that some
Mm-hmm.
internet. Thought there will be some lag in that.
Mm-hmm. But this is too much lag. Mm. Maybe I can stop sharing and share again.
Yes, yes, that will be better.
Oh, okay. I stopped sharing, but still this page is not moving. Hmm. This has got stuck, I guess.
Is it possible if you can log off and log in again? Then we can do it. Or
Maybe, but this should not happen. I am unable to understand like from where the internet issue is happening. Yeah, it has changed by its own now, right?
now you can share. I think some screen has
Yeah,
gone blank. You
I
can
did
share it now.
nothing. Like it is now, it's it is updating by itself. I think it will come just. But I'm actually not sure from which end the internet issue is happening. From my tabs end or from my.
I can
Yeah,
see the screen now. I can see
yeah,
the screen now.
it is now
Go ahead.
visible. So if I draw something now, no, no. Okay, okay, okay. Yes, it is coming. Anyways, okay, but it is very very slow. Anyways, so so we have currently talked about axial and bending, right? And we have not talked about shear. So what could possibly be the reason that we have not talked about shear and we have only talked about axial and bending? Any guesses?
Is it negligible?
Yeah, yeah, actually it is negligible. So what happens is we are talking about longitudinal members, right? So in
Hmm.
longitudinal members, the deflection due to shear would be very very less. Like you can even understand from your like we understand what is shear, what is the shear force, right? So if we cut a cross section here, and then we have a small element like this which
Hmm.
has some shear force like this. So
Correct.
now this will deflect like this. Okay. So the deflection due to this
But
phenomena.
there will be complementary forces in that other plane, right? If you are putting these shears,
Yes.
there will be a complementary shear on the top and bottom plane, but that
Ha
tries
ha ha.
to balance
Yes.
this force. Correct.
Yes. The complementary forces would be like this.
Exactly. So that
Hmm.
counters this deformation automatically.
Uh, no. Okay, the complementary forces that will be actually okay. So if this is the beam, if we take a section like this inside,
Hmm.
then the complementary forces will come along. But
Exactly. Okay.
if it is free surface, in the free surface there is no shear force acting, right? Just below the free surface there will be some complementary forces. Hmm.
Oh, okay.
Hmm.
Okay. I got
Hmm.
it. So
Hmm.
if it is okay, that complementary shear will
Hmm.
come into picture only for the internal.
Yeah. And with the complementary forces also there would be some deformation, shear deformation also. Like what happens is, say we calculate like this. So if this is V, say this is V plus delta V. So there is
Exactly.
slight more force in this
Mhm.
direction. So then this kind of becomes the diamond shape
Oh,
like
this the
this.
delta force will create this deformation
Yes,
in
yes,
that
yes, yes,
members. Okay.
yes. So this is how shear acts. So when we understand how the shear force acts, so now we can easily guess that the effect of shear would be very negligible in some long beam like this, right?
Agreed. Agreed. We see we never
Hmm.
calculate these deflections due to shear deformation whenever we do manually.
Yes,
See, this
yes, yes.
came up only when I was checking on that stat. In one of the
Hmm.
problem, I was getting some different result. Then I verified that. Then I asked the stat person. They said that no. That is because we are considering the shear deflection due to shear deformation also in their analysis engine.
Hmm.
That is what they said.
Okay. So if the beam is like this, say the length of the beam is this, the depth of the beam is this, then the shear deformation comes into play actually.
Deep beams, kind of a deep beams when
A
we do
deep
that.
beam, exactly. Very
Mhm.
deep beams and those cases, the shear deformation comes into play. So so this is the like basic idea on why we are neglecting shear deformation in our study so far, and when do we need to consider the shear deformation. So again, in stads and in stat I don't know, like sometimes what also could happen, I'm not sure, is like we define a lot of nodes, right? So if there is a node like this, so maybe this beam becomes a very short and thick beam. But actually we consider this beam together as one, right? So these are some small issues that might happen in STAD also, but I am
Mhm.
not an expert in this field. Don't
Mhm.
take my word and
No.
directly.
That's fine.
Yeah,
No.
but this I know this. Sometimes any redundant node or any node where you have not
That will be
give.
there. That will be there. Those
Yeah.
problems will be there. Generally, we avoid those things in while verifying the model or
Yes,
anything.
yes,
That
yes,
take
yes,
care of.
yes.
My
And then like
only
you can also define master nodes for the whole beam, and those things you can
yeah.
do. Hmm.
Sometimes we what are these floor slabs or the roof slab? We go with that master slab, assuming that all the nodes will deflect in the
Hmm.
same
Yes,
pattern.
yes.
So those
So,
things we. But in the matrix method, I mean,
hmm.
these stiffness is how they consider because we never discuss. I never seen in any of the textbook these
Oh,
stiffness. How it is plugged into their analysis engine. Stat.
okay. Stiffness due to the shear deformation, how it is plugged into. Okay. I'm actually not sure. Today, whatever
No
I'm,
issues. No issues. No issues.
yeah. No. Yeah. So today, whatever I was going to discuss was like how do we calculate this shear
Okay,
deformation,
go ahead. Yep.
and yeah, and then how it is implemented. I let us think, like, after we get the answer. But
Take your time. Take your
it's
it's
yeah, yeah,
take
yeah.
your time. Okay.
No problem. So now this shear deformation, how do we calculate shear deformation? We calculate by energy method, not by the classical elastic beam
Mr. Mahesh,
theory
again,
method.
sorry if I'm asking some out of context
Yes,
discussion.
yes, yes.
If I'm asking some questions out of context, sorry for that. So,
No, 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 no issues, no issues. I am enjoying these questions. Like,
okay.
I like to be like, what to say. Means I enjoy when I get to hear different questions. Like,
Okay.
otherwise it becomes boring. So it's always good to keep thinking, right? Anyways, so I enjoy a lot these questions. No worries, please don't worry. Anyways, so coming along to the shear deformation. So say this is the beam element which we are talking about. These are
Mm-hmm.
the shear forces. This is the deflected shape. Say this is what they call it, not delta. This is gamma. So this gamma is actually the uh, shear. Okay, let me define what is gamma. So say if this is dx, okay, this is the shear deformation dy. So we can say that dy equals to gamma dx,
Mm-hmm.
right? So now what gamma becomes? Gamma becomes dy by dx. So if this is dy is the shear deformation, dx is the length of the segment, then dy by dx is gamma, which is the shear strain. Okay.
Okay.
Okay. So this is the shear strain. So now considering elastic response, what happens is tau equals to g into gamma, where tau is the shear stress, g is the mm, modulus of elasticity, not shear
Rigidity.
modulus, modulus, yeah, shear modulus of the beam.
Rigidity.
Hmm. Shear modulus. So this is clear, this is clear. So now basically what we have to do is we have to find out these shear stresses and these things, and then we need to find the strain energy due to the shear force. From that we will find the deflection. So let's find out what happens is, so now tau equals to g into gamma. So and gamma equals to, then from here actually, gamma equals to tau by g. So from equation 1 what we can write is dy equals to tau by g dx. This is okay.
Mm.
Okay, so now how do we calculate shear stress? Shear stress is actually kv by a. This is shear stress for a beam. This is from strength of materials class in some undergraduate
Mm-hmm.
course or
Clear.
something.
Clear.
So what the idea behind this shear stress is, like, basically what happens is shear in any beam section varies like this.
It varies
Yes,
from the neutral axis. Yes.
it varies from the neutral. It's maximum at the neutral axis and varies like this. Okay, so now
Mm-hmm.
the average shear stress over the section would be v by a, total shear force by total area, cross sectional area. Okay.
Yes.
Yes, but there are various factors with which we have to multiply to actually get the shear stress around the neutral axis. Okay, so these factors
Mm-hmm.
are actually k equals to 1.2 for rectangle, then K equals to
Yeah,
10.
in the mechanic there are some variations of different formulas or factors are there for that
Yeah, yeah,
shear.
yeah, yeah, yeah. So this is how basically we find the shear stress. So
Hmm.
now once we have the shear stress, so what our dy becomes from this, from 2, dy becomes k v by a g into dx. Fine. So now can we remember the formula for not formula, like the concept for strain energy? So concept for strain energy is uh, virtual force V, small force V, multiplied by displacement dy. Or this could be opposite also, a virtual small displacement dy multiplied by the force induced V. This
Hmm.
is the strain energy of the member. Okay. So now if we integrate this strain energy, we get the total energy in the beam as 0 to L V V G A into dx, where the small v is the uh, shear force. Shear force induced due to a small virtual, small is also redundant word, due to a virtual displacement. Okay. So now can we remember the Castigliano theorem on so the Castigliano theorem, what it mentioned is, say there is a beam like this and you put a small unit load at this point. So the deflection of this point delta would be how much? It would be the strain energy developed in the it would be like you are calculating the deflection at this point for a unit load 1. So what is the work done by this unit load and displacement? 1 into delta,
1
right?
into delta.
Yeah.
Yes.
Equals to the strain energy. So that is equal to 0 to L K V V G A dx. Now here everything here what do we not know from here? We do not know is this small v. How do we calculate this small v? We calculate this small v from, say, this unit load 1. If this is the unit load 1, what will be the change in the uh, change in the virtual shear force diagram of the beam.
Hmm.
Okay. So this is how we calculate this delta. So this is how we calculate the deflection due to some shear. So the deformation from shear. Okay. So now how it is incorporated in STAD using the stiffness
Yeah.
concept, that is something which I am not aware of, and that we can, that okay, that is a good question that I can check upon. I can try to find. I will, and let's hope I find it, and then we can discuss in next class. Okay.
No issues. No issues. Yeah.
Yeah. Yeah. But very good question. How this? Okay. So, but the like basic concept of shear deformation is like this, and uh, the usual method of elastic beam theory does not work. Like here, we need to use some other methods like the energy method to calculate the deformation due to shear for a like for a beam or any kind of frame element or anything. Okay, so this part
Yep.
is clear, and the actual question I will look into it, and I will try to find it. If I find, then I can
Sure, sure.
share in the
No
next
issues.
class. Okay.
No issues. No issues.
Yeah,
No
okay.
issues.
So this was all about the shear deformation. Now let's move into the problem. So I guess this is also one important part. I don't know. If you are into developing your own codes, then this is a very important thing, like understanding the problem uh, using some codes, Scilab in this case, Skylab in this case. So this is the problem that was given in the last year's assignment. Um,
Mhm.
Here you have a truss of how many members? You can see I have just the problem is this part. This is the problem, and this is the solution. Okay.
Mhm.
So I have just copied the
Okay.
solution so that I don't have to draw the degrees of freedom. So we can see there are
Agreed. Agreed.
yeah, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 degrees of freedom. Okay, 16 degrees of freedom. This is the truss problem. So, and how
Mhm.
many joints are there? There are 1, 2, 3, 4, 5, 6, 7, 8. 8 joints. So 2 degrees of freedom per joint. 8 joints, 16 degrees of freedom. How many members are there? There are 13 members. Okay. So these are important information which which will actually control your programming structure, like
Yes.
how many unknowns are there, how many knowns are there, and all those things. Okay. So now from the given problem, which are the degrees of freedom that are constrained?
1, 2, and the 9, 10,
Yes,
and
exactly.
both are pin end.
Yes, yes,
Okay.
yes. 1, 2, 9, 10. And then these are constrained degrees of freedom, and then what else? So so in this case, the known displacements are at 1, 2, 9, 10, right? UK matrix. Hello.
Can you hear me, Mr. Banerjee?
Yeah, 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 I can hear you now.
Okay. 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 Okay.
Yeah,
There is some problem in the net. Okay.
yeah,
Okay.
yeah, yeah, there might be some problem in the hotel internet, but
Okay.
nevertheless
Okay.
it's
Go ahead.
hmm, hmm, but it's still working. I am happy. So because this is completely out of my control. So anyways, so now what I was telling is that um, the known displacements, those are in which degrees of freedom? 1 to 9, 10. And
Clear.
the unknown displacements, those are in which degrees of freedom? 3, 4, 5, 6, 7, 8, 11, 12, 13, 14, 15, 16, like all the rest of the
Remaining joints.
degrees of
Yes.
freedom. Yeah.
Correct.
So I have written that, but that has not showed up yet. It's very bad.
No, I can see that numbers 3, 4, 5, 6, whatever you have
Yeah,
written.
but after that also I have written all of those, but okay. But now I'm scrolling and that is also not visible. I will just stop and then share again. Yeah, it is visible now, I guess. Means it will come now. Mhm. So the known degrees of freedom are 1, 2, 9, 10. There we have the
Hmm.
known displacements, and the known forces are in all the other degrees of freedom, right?
Agreed.
So
Agreed.
the displacements and forces are like complementary to each other. So now let's start with the program line by line. Okay. So first line what they have done is CLC and clear. So CLC and clear are basically hello, am I audible? I guess.
Yes, yes, yes. Go ahead.
Okay. Okay. So CLC and clear are basically like programming. What to say? Manners. So CLC actually clears the output screen, and clear means all the variables that are stored from earlier. Those are cleared. Okay. So that there are no there are no random values or anything like that. Everything is cleared. There is no
Agreed.
nothing at the beginning of the program. So then nodes, we are writing the nodal coordinates. Okay. So this is very important. So here we have how many nodes? 8 joints. So 8 nodes, joints or nodes. Okay. So
Okay.
these 8 nodes are defined as 1, 2, 3, 4, 5, 6, 7, 8. Fine.
Mm-hmm.
And these nodal coordinates are defined in this node matrix: 0, 0, 20, 0, 40, 0. Can you follow how these nodal coordinates are written?
Yes, 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 yes. Clear, clear,
Yes.
clear.
Okay. 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 So basically, what does this mean is there is 1, 2, 3 till 8, one vector like this, say.
Which is the node number 2 in your sketch? I am not seeing the dimensions
Uh,
there. Is it the node 2?
Here, 1, 2, 3, 4 are going at the bottom line from. Is
What is
it
the
visible?
length of that truss? Where it is written? Yeah. Where is the
This is
length of the
1, 2,
truss? It
3,
is
4.
written.
Length of truss is here 20, 20,
Okay,
20,
20,
20.
20. Okay, it is 80 meter
15
length.
centimeters.
Okay, clear.
Yes,
20
yes,
0 is
yes.
right. Okay, fine.
Yes, yes. So basically, what this line node equals to this does is 0, 0, 20, 0, then 40, 0, then dot, dot, dot. Last one is 20, 15. So, what this does is this has actually correlated these numbers 1 to 8 to the x and y coordinates of the different nodes.
Agreed, agreed.
Okay. So now anytime if we want to know what is the nodal coordinate of say 6, so what is the x coordinate of 6, so what we'll do is we will find node 6 comma 1. Why 6 comma 1? Because here we are writing x and y, but actually any program, they don't understand what is x, what is y. They only understand 1, 2. This is 1, this is 2, this is 1, 2, 3, 4, dot, dot, 8. So this is a 8 cross 2 matrix for them, for the
Mm-hmm.
program. So now
Clear.
the program understands it's like this, but we understand it physically. What is the x coordinate of node 6? But when we
Mm-hmm.
require it from the program, we have to tell the program that give me value at this point. So how we will tell the program? We know we have numbered the nodes in ascending order 1 to 8. So we want the sixth node, and which coordinate do we want? X or y? We want the x coordinate, so 1. Okay. So the your value of node at sixth row and first column will give me the x coordinate. This part is clear?
Clear,
Yes, yes.
clear, clear.
Uh, uh, I am stressing on this trivial thing because in programming, just understanding how these variables correlate with your actual problem, that will make
Yes, it's
everything
better.
clear.
Yep,
Clear. Yeah.
yep, yep.
Yeah. So now the second member initialization is the members. So here what they have done is they have defined which are the member nodes. Like there are 1 to 13 members. Okay, and for all those 13 members there is one first node and second node. Okay, so again through this member matrix, what they have done, they have defined a 1 to 13 like this, correlating, say 1 2 2 3 3 4 dot dot dot, the last member is 3 6. Okay, and this 3 6 I have written from seeing the figure up above. Okay, so what they have done is, for every member, what is their first node and what is their second node, they have found, and they have stored in this variable called member. Okay, so now we have a major information on the geometry of the structure. We know what are the coordinates of the different nodes through this 8 by 2 matrix, and we know how the members are connected between these nodes with this 13 cross 2 matrix. Fine.
Yep, yep, clear.
So basically these two define the geometry. Now the next part what they have done is, they have found, they have defined a variable number node, size of node comma 1. So number node, by number node they mean like what are the total number of nodes. So by total number of nodes, there would be as many nodes as they are defined the coordinates. So this size, actually what the size does is, size gives you the total number of elements in a vector or a matrix.
Hmm.
In a vector actually, not a matrix. So because it is a vector, so they have done comma 1. Okay, so y comma 1. So this node, this node variable, this is actually a matrix, right?
They're defining a matrix size, 8 by 1 or 13 by 1 or something like that. In that, one is the column.
Yeah, so one is the column within the matrix node whose size they are
Node
wanting
matrix
to
and
find
member
out.
matrix. Yes,
Yeah.
yes, yes.
So
Okay.
so basically, they what they did is, they selected a vector of all the x coordinates of the nodes, and they counted how many x coordinates are there. So as many x coordinates are there, that many joints would be there, that many nodes would be there. Okay, so they have,
Mm-hmm.
by this method they have found the size of the node, size of the number of nodes. How they have found the number of members? Again simple, as many first joints of members are there, those many members would be there. So again size of member comma 1. Okay, number of degrees of freedom, how they have found? So as many joints or nodes are there, multiplied by 2. This part is fine.
Yeah, yeah, clear.
Yeah. Okay, so now they have defined the member properties. So they have defined elastics, modulus of elasticity as E as this and A as this. Basically they have provided EA value as this, so you can assume that A is same for all members as unit, so E becomes this.
No,
So
if it is two different metal, how to define that here? How to give the command? Can I, is that
two different
EA? If it is
metals,
two,
like every member
two
has
different
different kind of
are two
AE.
different areas. Okay, how to define that in the code?
Means you mean that every element has different AE
A,
value?
mean, for example, if I had different angle sizes, how to define that in the code?
Yes. So in that case, your this E or A will again be a matrix containing 1 2 3 to 13 values for the 13 members. Okay, so you will have 13 E values for the 13 members, 13 A values for the 13 members. Then when you will use AE later, where they have used AE, let's check. Mm, where have they used AE? Anyways, yeah, here, where they have used AE. So have they? Oh, actually they have defined that. I'm sorry. Hmm. So here you see this E. This E is not a single member. This E is from 1 to number of members. Okay. So when we are defining say node or member, we just wrote node equals to this. Okay.
Mhm.
But in this case they have written e, then in bracket 1 to number of member. How, what is number of member? 1 to 13 equals to some value constant. Okay. So what does this
Okay.
mean is they have this 1 to 13 value of e, they have this particular e which I
Mhm.
was mentioning, but here everything is constant.
Say, for
Everything is
example, if
constant.
the member number 6 has got a different E, how to
Yeah.
define that?
So if member number 6 has a different e, so you define this constant e for everything, then you write another line that e of 6 equals to say 10 to the power 5 or
Then I
so.
need to, in that case, I need to list out everything. Except 6, I need to list out everything.
Yes.
1, 2, 3, 4, 5, 7, 8, 9, 10, 11. I have to
No,
define like
like
that.
the first part remains same. Here everything remains same. Like you have same E for everything, same E and A for every member. Only 6 you
Mm.
have a different E, right?
Okay.
So what you do, you define 6 also with the same E that you have already got. Okay, you define everything with the same E what you have already got.
Hmm.
Okay, now you want to change the value of E for 6. So what you
Correct.
do, you just pick out E of 6. So again E
Hmm.
of 6, and like here already I discussed node of 6 comma 1. These are single values.
Hmm.
These are values at one place of that matrix. So you just pick
Okay.
E of 6 out, and you say that E of 6 has to be this value and not the previous value. So whenever you do one single equal to one, this is actually in programming. Are you acquainted with programming, or like this is
No, no, no,
mainly new?
not nowadays. Not nowadays.
Okay, no problem. So what happens is in programming we have different kind of statements. So when you like a when you write a equals to b, this is an assignment statement. Okay,
Hmm.
so the value of b is assigned to a. Okay, so no matter what a was earlier, or what either
It
there
takes
was
the last
any a or
statement. It
not.
takes the last statement. It takes the last statement.
Yeah, it just
Kind of.
assigns the value of b to a. It does not
Agree.
care whether a existed, or a had some value, or a was something else. It does not care. It is not like when you have the same file, file name, and you try to copy it, and they will ask you whether you want to copy and replace, or copy or do those things. It is not like that. It will always copy and replace. Like it is always assign the value of b in a.
Okay.
Okay,
Clear.
so this is assignment statement. And if there are two equals to say uh, a equals to b, this is a logic statement. So a logic statement here, it checks whether the value of a is equal to b or not. So these are different kind of statements in programming languages.
Agree. Agree. Agree.
Okay,
Agree.
yeah. So now you see most of the things are assignments, whatever we do in program. Here these nodal coordinates are assigned to the variable node. Here this member join coordinates connectivity are assigned to the variable member. Then these number of nodes, number of members values are assigned here. And similarly, if you assign some value of e6 and then you want to change that, you can just directly change by assigning it specific location. I guess
I can
again,
keep change. Yeah, again, it has stuck that screen.
yeah.
So E6, E7, E8, I can define if it is changing.
Yes,
But
yes,
first
yes.
statement remains same. E of one bracket one comma member number that remains same. That is one,
Uh,
irrespective of everything. Then I
yeah.
can define whatever wherever I want to change. I can specify that member number and I can give that value there in that.
Yes, yes, yes. That is the way I told you, because there was only one member which is different. Okay, so say if every member is different, so instead of writing it like this, you can easily write it like this: node or member, right? Like you have written node equals to a lot of values by
Mm-hmm.
using semicolon. So instead of
Okay.
writing every time, you can write all the values with these semicolons. Then you can define the values of e.
I can write at E within the bracket. I can define eight
Yes,
numbers or 30 numbers in sequence. If it, that has
in
to be in sequence
sequence.
with matching
In
with that
sequence.
number 1 to
Exact,
13. Okay, clear.
exactly. Yes. So again, the syntax here is when you have square brackets like this. Okay, it is, yes, now it will come. So when you have square brackets like this, and you write inside, say A, then you give a space or a comma and write B, and then you give a semicolon, and then you write C, and then you give a space or a comma and write D, say space.
Mhm.
So this translates to a variable. Say this is, I say this is variable var. So this variable var in the program, this has made two columns and two rows. Okay, 1 2 1 2. So first column is AB, and A comma B or A space B means they are in the same row. If you give a semicolon, they change the row. Then it becomes CD. Okay. So this is the syntax on how variables are stored. So when you see
Okay.
node 0 space 0 then semicolon 20 space 0 then semicolon 40 space 0 like this. So this is
Mhm.
stored like I have written in the right hand side 0 0 20 0 40 0 like this.
Okay, clear, clear.
Okay. Yeah. So now if you need your, so now what actually has happened is your E is also stored like this 10 to the power 9, 10 to the power 9, everything 10 to the power 9. Okay,
Okay,
so basically you can just write different values of E with separated by semicolons to define the C vector, and same goes for A also.
clear.
Okay, clear. So now next step is like initialization of the stiffness matrix. So uh, so first of all what we need to do is we need to define all the displacement vector, all the displacements as 0. Okay, this is a definition that all the elements of this 2 into number of node comma 1 matrix. Okay, this is a matrix. 2 into number of node comma 1 is a matrix. So what is number of nodes here? Number of nodes is 8.
Mm-hmm.
So this is a 16 comma 1 matrix. 16 comma 1 means 16 rows and 1 column.
One column, clear,
Yes. So again kg is 2 into number of node comma 2 into number of node. So 16 cross 16 matrix.
clear.
Okay. So now what they are doing is they are defining everything to 0. Why they are doing that? So for the unknown displacements, uh, like the known displacements are already known as 0, right? And the unknown
Mm-hmm.
displacements, they can just reassign those values and keep the rest as 0. Similarly for
Clear.
kg everything is 0,
Mm-hmm.
and then they are adding the specific stiffnesses at the locations on that 0. So when you add on that 0, then it actually turns out to be the final matrix. Okay,
Agreed.
but they need to have some initial value. The reason is what happens is why they are initializing as 0. The reason is, say when we write the global stiffness matrix, say we have a stiffness matrix like this and a stiffness matrix like this. Okay, k1 and k2, and then we add, then there is one common region here where we have
Clear,
to add
clear.
the
Yes,
values like this
yes,
here.
yes.
So this is how we do by manually.
Agreed. Mm-hmm.
But for computer to understand that this is common region and everything is that is very problematic. So what the computer does is the computer defines this length and this breadth of the matrix and defines everything
Mm-hmm.
as 0. Okay, and then on that 0 it adds the value of k1.
Agreed.
Okay, and then again on that k1 and 0 matrix it adds the value of k2. So it automatically takes care of the
Clear,
common region.
clear, clear,
This
clear.
is the algorithm. So now So we have initialized the matrices. Now we applied the loads at the degrees of freedom. So
Mhm.
again we initialize every load as 0, very similar to what we did in the stiffness, because
Okay.
most of the loads
Hmm.
are 0. There is only load at B and C which are non-zero, and there are the reactions which are non-zero. But again the reactions, let it be 0 for now, we'll replace them with the actual reactions.
Clear, clear.
So all the loads are 0, and we have defined only the load at P4 and P6 as the values that are given. Fine. Clear till now? So now,
Okay, I got a doubt there only. Got
yeah,
a doubt there only.
uh,
How the
yes.
program knows that degrees of freedom 4 is assigned to a particular joint?
Hmm.
I can change
Okay.
the degrees of freedom, right? I can change the
Hmm.
degrees of freedom number wherever I want.
Hmm. Hmm. Hmm.
How in the previous lines, how the programming assigning that P4,
Hmm.
4 is a degrees of freedom, correct?
Hmm. Okay. Hmm.
How it is assigned to a particular node, because my node numbers are fixed, because
Hmm.
I given the coordinates. Node
Hmm.
coordinates are fixed.
Hmm.
Degrees of freedom is a variable. Wherever I want, I can change the degrees of freedom numbers.
Hmm.
How
So,
computer is knowing that degrees of freedom 4 is assigned to a particular node number?
oh, okay, 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 okay. I get it. Okay, I was thinking that we have already discussed, but no, this is different. What we are talking. So, so
You got my
basically,
point. So that was
yeah,
the
yeah, yeah, I understand. So
because
basically, you see all the
degrees of
joints
freedom
that are
wherever I
defined.
want, I can change the number.
Yeah, yeah, yeah. No, we should not do that. So basically, wherever you see the joints are numbered, okay, uh, you can see the joint numbers, right? Hello, yeah, am I audible?
Okay, that is the point.
Uh-huh. No, I you
Can you
can
hear
see
me?
the joint numbers, right? 1 to n.
Yeah, I can see that. See, my
Okay.
question is, I can see that
Yes,
kind of 1, 2, 3, 4, 8 joints.
yes, I have understood your
Whatever the
question now.
degree.
Uh,
Okay,
yeah,
yes,
yeah. So we have the joint numbers 1 to n. Okay, and we
correct.
have defined the degrees of freedom as, for each joint the degree of freedom would be 2n minus 1 comma 2n.
Agreed. Now got it. Now I got it.
Okay.
Now that was okay.
Yeah, yeah.
So
So
the
this is never
point
mentioned
is
anywhere,
we have
but
to
later
give that,
on this comes. Yeah.
yeah, degrees of freedom has to
Mm.
be given with the joint numbers. Wherever that in the
Hmm.
ascending order only I had to assign the degrees of freedom.
Yes, exactly. Yes, yes, yes. So this is how you reduce one step in the algorithm. Otherwise, what you can do is, for each, like here, for each element we have defined the joint numbers. Okay. So again, for each joint you can define the degrees of freedom on that joint, but that would be a redundant. Like you are naming, you yourself are naming the joints and the degrees of freedom. So why not use a method where you can reduce this step? You can directly correlate your joint number with the degrees of freedom number. Okay.
Agreed, agreed. Now
Hmm.
I understood. So
Yes.
whenever you define that node number 3, I mean automatically degrees of freedom are assigned as 6 and 5 for that.
Yes, exactly. Perfect.
Okay. If I say it is 8, it is 16 and 15.
Yes, 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 yes.
Okay. So
That is correct.
16 is in X
And
direction, 15 is in Y direction. Is that
and that
number
comes
how?
along in the later part of the program also. You can see when we go. Like
Okay.
how that is taken care later on. You can check that.
Okay.
Hmm.
Because that is not written in that. I mean, when I started using this code, then
Hmm.
suddenly I got stuck in that P4. How? I mean, this program knowing
Hmm.
that this P4 assigned to that particular node.
Hmm.
Okay.
Hmm.
Now I
Hmm.
clear.
Right.
It
Hmm.
clear.
Hmm. So now similarly now you define the boundary conditions. Now I guess you know how you have
Clear. Clear.
defined the
Now it
boundary.
is clear. Yes. Yes.
Yes.
Yes. Yes.
So
Yes.
now
Yes.
initialization of the partition stiffness matrix. So again, like here we need to define two different stiffness matrices, K1 and K11 and K21, for the unknown displacements and the unknown forces. K11 for unknown displacements and K21 for the unknown forces. Okay. So this again, what is the length of U unknown? U known and U unknown we have
But I don't need
defined.
to define anything in K11, K21, right? I don't need to define anything in that K1. My definition will stop up to U known and U unknown and P, correct? I don't need to define anything in K11, K21 or anything, right?
No, you need to find the K11 and K21, right, to solve the problem.
No, that program automatically does that. I don't need to do anything in this. I don't need to give any inputs for this.
Oh, no, 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 no. Like you need to
Uh,
calculate the values of K11 through the program,
c-
not through your input.
correct.
Hmm. Okay.
Agreed, agreed.
Hmm.
Got
Hmm.
it.
So you just give what is the U known and U unknown value, and then
Exactly.
you
Yes.
define the matrix sizes for K11 and K21, and then
Mm,
the values of stiffness they actually get calculated in the program itself. So now moving on to the real part, like this was the definition of the problem. Now the calculation of the problem, how you calculate the stiffness matrix. So here we have written, here they have written that computation of member stiffness matrix and global stiffness matrix. So here for E equals to 1 to number of members. So this is actually a looping function inside the program.
mm,
Okay. So this
clear.
E is the counter for the members. So
Mm,
1 to
clear.
number of members. So for the 13 members, it will conduct this operation. Okay. That's simply what
Mm,
it means. And when it will come back, like there will be some end for this for. Okay. Where is the end for this for? Say there is. Hmm, there is this end for, there is this end for, there is no end for this for. So this is actually the end for this for. This is important because by this we know that inside this, inside these two arrows, whatever we have, that will go in loop. Like when your program starts going like this, say it goes here, here, this is like scribbling. You can see the dots, yellow dots.
yeah, clear, clear.
Yeah.
This loop
So
function is clear. Okay.
yeah. So it moves like this, and then before it ends, it goes back to the first function. Okay.
Mm-hmm.
So now in what they are doing for the first member. Now when we are talking inside the loop, we are talking member by member. So let's assume the first member. What they are doing for the first member? For the first member, they are defining I1 and J1. So what is I1? I1 is the first node of the member that is considered. So now E is the member that is considered. So for the first member, E will be 1. For the 13th member, E will be 13. That is clear. So I1 is the first node. Say for the 1, I1 is the first node of the member. J1 is the second node of the member. Is this clear?
Yeah, yeah, clear, clear.
Okay. So now they are calculating the length of the member. How do you calculate the length of the member? They have done the square root of node at J1 minus node at I1 square, node at J1 minus node at I1 square for the x coordinate 1 1 and for the y coordinate. So xj minus xi square plus yj minus yi square and whole square root.
It's clear,
Length is
clear,
clear.
clear, clear.
So now lambda x and lambda y, how they are calculating? Uh, Again, x lambda x
X2
is
minus X1,
uh,
Xj minus Xi
yeah
by L,
lambda
and
x
Yj
is
minus Yi by L. Okay.
lambda x is like jx minus ix by L, and lambda y is jy minus iy by L. Okay. So
Clear,
lambda
clear.
x, lambda y, they have calculated. Member stiffness matrix they have just supplied to the computer because they don't know structural engineering. We have to tell that, like how the member stiffness matrix is formulated. Like the member stiffness
Clear,
matrix
clear.
information we have to give. Okay. So this member stiffness matrix will be different for each member depending on their area, elasticity, and length, and also lambda x and lambda y. Okay. So so it is not the same for every member, it is different for different members. So now again what they have done, again they have defined I1 equals to member E1, J1 equals to member E1. This is I don't think this is required, this is something extra, because already we have defined earlier I1 and J1. Okay. So and but it is nothing wrong because we are defining the same thing. Okay.
Mm-hmm.
So next again I think my handwriting is not showing up. Anyways, so
I
next
can see the screen. Okay. Mm-hmm.
yeah, yeah. So next, degree of freedom for each member. So here comes your doubt, like what is the degree of freedom for each member. Now how they have calculated the degree of freedom for each member, they have calculated as the first degree of freedom as 2i1 minus 1, and the second degree of freedom as 2i1, third degree of freedom as 2j1 minus 1, fourth degree of freedom as 2j1.
Clear.
So this is clear now, right? Yes. So now they have the global stiffness matrix, which is for till the first member is calculated, it is actually 0 0. So what they are doing, they are just adding the different element stiffness matrices to the global stiffness matrix. How they are doing? Very simple. Like you already know the position. Okay, sorry. This is the global, say is 1 2 3 dot dot 16, 1 2 3 dot dot 16. So you already know the position of element 1. Okay, by what? By I1. You already know the sorry, you already know the joint 1 of the element by I1. You already know the joint 2 of the element by J1. You already know the member degrees of freedom by this vector, by this matrix. Okay.
Mm-hmm.
And then what does this mean? This will actually give you some values, say 1 2 3 4, or say 3 4 5 6, or say anything. It could be 6 2 1 3, anything, 5 2 1 3, anything. This will give you some values. Okay. What this program will do later on is it will go to those values. This what it has done. Next we have run two different loops. One loop is for the rows, one loop is for the columns. Okay. And what they have done is the value, this is member degree of freedom vector. So for member degree of freedom of 1 comma I, what is I is the outer loop value, and comma 1 comma j, what is j is the inner loop value. Okay. So say when I equals to 1 and j equals to 1, it means that the kg value at degree of freedom 1 comma 1. Okay. So let us assume for the for understanding, let us assume these are 5 2 3 1 member degree of freedom. Okay.
Mm-hmm.
Okay. So so what is the kg value at member 5 comma 5, right? So at member 5 comma 5 it is initially 0. So what it does is it takes the initial value, it tells that now the kg value of member 5 comma 5 would be the kg value of member 5 comma 5 plus the element stiffness matrix of I comma j. I comma j means the first element of the element stiffness matrix. Okay. Now
Clear.
j,
Clear.
now j changes to 2. Say j changes to 2 here. So now what it means that what is the element stiffness, what is the global stiffness matrix at 5 comma 2, because j is 2 at 5 comma 2. So it will go somewhere here, say somewhere here, and it will add the value there. Okay. So what it will do is first it will add all the elements at the fifth row, and then it will go to the second row. It will add all the elements at the second row. Okay. So this is how it will complete the whole matrix, and this loop will go on for all the members. This is clear?
Yeah, yeah.
Yeah.
Hmm.
So it is not so easy to understand. Like, you are smart enough, but I
No,
think.
logic is clear. Logic is
Yeah,
clear. I
yeah, yeah,
understood
yeah,
the logic, how it is
yeah, yeah, yeah,
running.
yeah. So like, many people face problems in understanding this part. Yes. So but I'm happy it is clear. So now, so this part is the, like, most of the programming done. Now what they have done is partitioning of the stiffness matrix and the load vector. So what now you have to actually find out that which are your k11 and which is your k12, k21 or k12, whatever you call. Okay. So how do you find out that? So you you run a loop from you run this loop you run this loop from 1 to the total number of unknown what to say, unknown
This,
displacements. Okay. So you run this loop. Inside that loop, what you do for k11, uh, let's let's see what is k11, k21.
take that row and column separately. Make a separate matrix for that.
Yeah, 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 exactly, make a separate matrix. So say there are three unknown, no, why say, we know that how many unknown are there. How many unknown are there? There
There are
are
three. What we gain that one
12.
for
12
four,
unknown.
four, four,
Huh?
12 unknowns. Yes, four known and
4 known, 12 unknown. So there are
yes,
12 here. Okay. And there are 4 here. So your k11 would be how much? K11 would be 4 cross 12.
four cross two. Yes, no,
Yes.
four cross 12. No,
To 12 cross 4. Sorry. 12 cross 4? Or 4? I am getting
no,
confused.
row is four only. It is
Just 1 second. Row is 4 only. Yeah, row is 4. What are the.
because your unknown known displacement is four. It has to pick that four rows
Mm-hmm.
partitioning.
The unknown displacements are 12. So this will be 12. That's for sure. This will multiply to that, right?
Will it be four by four? What it
I'm getting
takes?
confused. Just 1 minute. Here we have the P known and P unknown. Okay. So now P known is 12 and P unknown is 4. U unknown is 4. Okay. So to find this 12, this will be actually 12 cross 12, right? It should be 12 cross. Yes. It is correct. It is correct. Yeah, I was getting confused. This will be 12 cross 12 and this will be 4 cross 12. K21. This is clear. So we have 12 known forces here. So 12 rows and 12 unknown displacements. So 12 columns. 12 cross 12. And here we have 4 unknown forces. So 4 rows and 12 unknown displacements. That is 12 columns. 4 cross 12. It is clear?
Yes, yes.
Okay. So now what they do is they unknown displacements are 12. So they run a loop from j equals to 1 to 12. That goes to 12.
One. How come it is you unknown will be in the first 12 rows? Why not other way? I mean, what is the logic?
No. Here in this matrix that will not be the case. I am just talking about our understanding, our theory. What they will do,
Okay,
that
okay,
will be very different. Yeah.
okay. Clear.
In this matrix, you will not get a partition like this. In this matrix, what they will do is they will just catch which are the unknown forces and unknown displacements, and they will
Agreed.
pick up
They'll
randomly to
check the
form
each
the
element
matrix.
and they'll
Yes.
pick that numbers, pick that
Yes. Yes.
stiffness.
Yes.
Okay, clear.
Yes. So they are actually doing the same thing here. They are doing for I goes to for first they are counting j from 1 to the length of the unknowns, then they are going I from 1 to again length of the unknowns. Okay, why again length of the unknowns? To find k21 12 cross 12 matrix. Okay, so length of unknowns 12, again length of unknowns 12. Okay, so now k11 what they have defined is, they have defined this one. So you know the unknowns, they have defined the different joints for unknowns, right? So they just pick the values at the joints of unknowns. Okay, is this clear? So they just pick the
Yeah,
values at the different joints of unknowns.
yes.
Yes, and they form k11. So now next for k21 we have a 4 cross 12 matrix. Okay, so here we, our outer loop was already 12, which is the number of rows, but the columns are now only 4. So the u known, and what are those columns? That are the kg values at u known comma u unknown. Okay, so basically what they have done, they have skipped the row operations to uh, make the partition like this. They have
Is it
just picked
difficult
out
to
the
write
values
the? Is it difficult to write that coding for that changing the
for row
rows and
operation.
column? Is it difficult? No, I'm just
I,
asking.
mm, it is actually not very changing
I
rows.
don't think it is
No,
difficult,
changing row
right?
and columns it is actually very easy, but then
Yeah. Then
it
they
is
can pick that
redundant. Like it.
K11, K21. They can pick that right instead of all these things. If they write a code to change the rows
Yes.
and then you can easily pick that K11 and K21 from.
Yes, yes, yes. That is possible. I agree. But this is also like one. I am not sure actually which method will take more time. But I maybe that method also could take more time because every time you have to do some operation on that.
I know. Something
Yeah.
has to go into that coding language, so then only they'll understand which is easier and which is.
Yes, 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 yes. But both are possible. Like both are correct. It is not very difficult to change the rows and columns also. Uh, yeah, but one thing. Yeah, but one thing. Like to change the rows and columns value, I think it will require more time. The reason is
More loop commands is required for
uh,
like that each.
no loop. I am not sure, but more space is required. You need to define a new global matrix because
Mhm.
you we replace it like this and like this, but here everything is assigned. So if you replace one like this, everything is that data is lost. So you cannot replace in the same variable. You have to define a new variable, right? Or you have to store this row first somewhere and then replace it, right? So you need more space.
I mean,
Mm.
it doesn't go to my head. Okay, leave it. Okay,
Yeah, yeah, yeah,
so much.
yeah.
I can understand the logic and essence. I
Hmm.
understood that logic and
Yeah,
essence.
yeah. I think this is a better, like, easier method. Yeah. Hmm. Anyways, so now what they have done is, next the p known of j equals to p unknown of j, load vector. What they have done here, p known. Okay, now. So now they have found the k11 matrix and k21 matrix, but there is one more thing that is required, that is the pk matrix, right? To solve.
Load vectors. Yes.
Yeah. So p known is actually wherever u is unknown, that value of p they have stored as p known. Okay, that is clear. So wherever the u unknowns are there, the corresponding p's are actually the p known values. Okay.
Hmm.
Okay, so that's clear. Now nothing. Now they know p known, they know k11. They just solve for uu, and they get the values of uu. And again they just solve for pu equals to k21 into uu. They get the values of pu. Okay, for the member forces what they do, they go for so this is actually the loop to get the unknown displacements. Like they wanted to keep all the displacements together, So they just placed the value of EU to the total displacement vector. Okay, nothing else. Hmm. So understood, right? This is UU is the
Yeah.
displacement that they have found. They have just placed it in the global displacement vector. So now the member forces, again what they have done is they have calculated the different members from, they are going from member 1 to 13, and for each member they are again finding the local stiffness matrices, and using the local stiffness matrices and the u at that member degree of freedom, they are actually calculating the forces. This is very simple, nothing complicated, like whatever we have discussed is a part of that. Okay, and they have plotted the deformed shape. This is not very important. However, I feel that I have done one modification in this code, is that okay, this was actually the code that was given in the, you have downloaded the code, right? Yes, you have
Yes, yes,
downloaded.
yes.
Yes. So this is actually exactly same as the code that was given. You don't have to change. That was the code for the previous year's assignment itself. Okay. Now, uh, I have changed one thing in that code. You have also run that code, I guess, and you have got all the answer. But you could see this deform shape was not there, right?
No, I didn't check that because I didn't really run that program because it got stuck in the degrees of freedom, how it
Okay.
is taking that number. So now I have to do that now.
Hmm.
I
Okay.
have to do
So
that.
when you will run the program in the last case, you see they have given the final answer. You see both the deformed shape and undeformed shape actually matching over one another. Okay,
Mhm.
you cannot visually see the deformed shape. The reason was, what I found is, when they are plotting, they are using a factor, a scaling factor, and the scaling factor is
Mhm.
very small. They are using some 0.25 scaling factor. So as it is, if a truss has to deform such that it is visible,
Exactly. The
it is
scaling has
it
to be
it is
scale
not
has to be more
possible.
to see that. Yes, yes, I
It
agree.
has to be exaggerated to see. So I just changed that 0.25 to 1000 so that we get a very nice deform shape like this. This adds so much meaning to the whole problem. We can
Agreed,
see, yeah.
agreed, agreed.
So that was all. And these are the variables that you will get. These are all the displacement, the displacement vector u. These are all the unknown forces, pu. These are all the forces, are the 13 member elements, f. Okay. I think now there is no problem. There should not be any problem with the
No, no, no
program.
problem. But only thing is, what, how to this plot shape automatically it gives, or what is the? I need to give any command to.
Plot shape. There is some syntax to that. Uh, Basic syntax like.
Where do I get those syntax to get that load vector, displacement vector? Where do I get that syntax for that command? Or I have to write
Oh,
that
load
u
vectors displacement. Okay,
enter
okay, okay.
kg
So
vector.
this was the entire program. When you just run this program,
Hmm.
you
Run
click the
means what?
run button.
F5. I run that. What?
Huh?
Where is it? Run button? Yeah. I don't know. I have
Is
to just check that.
so you open the program. That is the editor window. Okay. So in
Hmm.
the top there would be some run button like this play kind of button.
Okay.
So
Hmm.
you run that, and automatically one screen will pop up with this image, because this has been plotted.
So automatically it comes shape. Okay.
Automatically
Fine.
it is
Fine.
comes. And but these variables, these will not pop up. So there are different windows. There is one editor window, there is one variable space. Okay,
Hmm.
so this is on the separate window. There is one variable space where you can see different variables lined up together. So these I have just you can see different variables, say a b c d f something something, and beside that there will be written that this is 1 cross 2 matrix, 2 cross 4 matrix, something something like
Okay.
this.
Okay.
So
Hmm.
when you just double click on f, and you can open this one, you can see what is the
Clear.
values
Let
of
me
f.
try that. Yeah.
Yeah, okay. Syntax is pretty similar, pretty simple. So this was all about the trust problem. The beam problem, I am not discussing it in those details because everything is similar. You first define node, you define member connectivity, number of node, number of member, number of degrees of freedom,
Here
Then
also
the
the degrees of freedom, same logic. That is
same logic,
predefined.
same
Degrees of
logic.
freedom locations are
Yeah,
predefined. Okay, clear.
1 2 3, 1 2 3 4 5 6, same logic. Yeah, again member properties again same. Then again initialization, stiffness and displacement metrics same. Fixed end moments is something which is extra here, but basically nothing. Fixed end moment is just another,
Clear.
like we are defining another p and then adding the p with the p1, p dash with p double dash gives p, something like this, nothing else. Like fixed end moments you have to supply, you can calculate, but it is very simple problem they have supplied, I guess. They could have calculated with by giving the load and then the length and those things also, just by using the formula, but they have supplied. Okay, then again load vector same. Then nodal load vector you have to, yeah, what I was saying, this p equals to p dash plus you have to just add the fixed end moments at the different what to say, different points. So for each element you have to add the fixed end moments at those respective element degrees of freedom. Okay, pretty simple. And then again define boundary conditions similar, define k11 k21 similar. Matrix assembly is actually absolutely similar. Degrees of freedom again similar. Global assembly of the matrix similar. Partitioning of the matrix similar. Then solve and then find the answer. They have not plotted in this case, so just find the different displacements and different forces. So I guess there is no need to like take this up again in the next class. So
Fine.
pretty similar. Yeah. So basically for now, week 7 live session is now complete and week 7 course also is now complete. So after completing 7 out of 8 live sessions, we have got into sync with the classes. Anyway, so this was all. Then next class we can, first I will check how that is implemented in Stat Pro and similar softwares. If I could find, I could tell. Otherwise,
No issues. No
unfortunate.
issues.
Yeah.
No issues.
And then we'll see whatever is done in the 8 week lecture. We can discuss that, and we can also have some summary of like anything you want to ask. You can ask
Sure.
because that will be the last class. Yeah.
Sure. Sure, Mr. Malik.
Okay.
Okay.
Okay. Yeah.
Thanks.
So
Thanks, Mr. Malik. Thanks. Bye. Good night.
yeah. Okay. Bye. Good night.